time for our section to begin. First of all, I would like to greet and invite Associate Professor Thani Sivongchai, Dean of Faculty of Agriculture, Kasetsart University, to deliver welcome speech. Please, Dr. Thani.
Ladies and gentlemen, good afternoon, and welcome to the forum on list on crop production under the climate extreme. In today's world, the climate change has become a press issue that requires immediate attention. It's imperative that we work together to find solutions to mitigate its effect. This forum provides a unique opportunity to bring us together to discuss the challenges and opportunity presented by climate extreme on the crop production. Today, we are privileged to have with us two speakers who have dedicated his career to pursue the climate action. Our speaker, Professor Simon Wang, the professor from College of Agriculture Applied Science, Utah State University, and Dr. Gorn Petayun, Director of Geoinformatics Production Innovation Office, Geoinformation and Space Technology Development Agency, GISDA. It's my honor to invite Associate Professor Sukhet Nakasathian, the Vice President for Research and Creation, Kasetsart University, to officially open this forum. Without further ado, please join me to welcome the Vice President to the podium, please.
Ladies and gentlemen, I'm honored to welcome you to the Forum of Risk on Crop Production under the Climate Extremes. As we gather here today, we do so in recognition of the urgent need to address the pressing issue of climate extremes. We know that our planet is facing unprecedented challenges, and we must take this action now to ensure the future for the next generation. Climate extreme is not just an environmental issue, but a societal one with far-reaching implications for our health, economy, and security. It is a problem that demands our collective attention, commitment, and action. Our speaker, Dr. Simon Wang, my long-lasting friend, long-term relationship with Kasetsart University. He's going to be one of the speaker this afternoon. As Dr. Thani already mentioned, that he's from Utah State University. For this long-term relationship between Kasetsart University and Utah State, I think this is a good sign that we can keep the relationship and transfer the knowledge to the following generations. Dr. Parichat, who's a chairman for the plant session, she is also the graduate from Utah State and also the student of Simon Wang. So this is like we have a long supply chain from Utah State. And his talk on facing climate risk and extreme will reveal the situations that we should aware of encountering globally. This forum is not just for acknowledging the problems, it is also about finding solutions, sharing knowledge and experience, exploring innovative ideas and practices. The talk on climate change issue, the extreme weather events, and major impacts on agriculture and natural physical environment from Dr. Pakon Petprayun, the Director of Geoinformatic Product Innovation Office or GISDA, and under GISDA, will provide the insights and discuss strategies that can lead us towards a sustainable and equitable future for food security through agricultural production under the climate extreme circumstances. As well, that we also have the memorandum of understanding with GISDA and Kasetsart University. And we also gather the researchers who would like to work with GISDA and group them into different clusters, communicating with GISDA. I think this is very good side, Dr. Pakon, that we can have the fruitful project between Kasetsart University and GISDA in this near future. As we must work together to achieve meaningful change, and we must do with a sense of urgency. The stakes are high, but we have tools, knowledge, and capacity to rise the challenge. I am confident that the discussion and collaboration that will take place during this forum will help us to identify practical solutions and move us closer towards a more sustainable future for agricultural production. And this morning, our President, Dr. Chongrak Wachalinrat, just announced that Kasetsart as a green university and moving towards the carbon neutrality in 2035. So there's going to be a lot more activity related to sustainability under the Kasetsart University policy too. And so let us begin for this forum with a spirit of openness, engagement, and determination to take bold actions towards a more sustainable future. Thank you so much. ขอบคุณครับ
Thank you very much for warm welcome from Associate Professor Thani Sivongchai, and also very important words delivered from our Vice President Sukhet Nakastian to highlight about the importance of climate extremes and the events that gonna be impact from the climate extreme. So before we begin the presentations from our guest speaker, I would like to invite Vice President Sukhet, Dean Thani, and also Director Warapha to be in front of the stage. I would like to say thank you before presentation. Would like to thank you to our guest speaker first and giving some souvenir. And after that, we would like to invite all to take a group photo together, please. So first of all, we would like to invite Professor Simon Wang, please. Yes, would like to give a souvenir first. Yeah. Yes. I think that after we giving the souvenir, we will take photo again together. Yeah. So second, I would like to invite Dr. Pakon, please. And please, Dr. Next, I would like to invite Dr. Simon Wang to take group photo together, and all our Dr. Pia, Dr. Pasji. Yes. So thank you very much. Okay, thank you very much. I think this is our time for a presentation. So the first talk, I would like to invite Professor Simon Wang from Utah State University to give his talk about facing climate risk and extremes. So after presentation, the first presentation, we're gonna continue for the second presentation. If we have any questions, please keep it for the last after second presentation. Thank you very much and enjoy the presentations from Professor Simon Wang.
Thank you, Ajahn Noi. Hello, everyone. My name is Simon Wang. I go by Simon. My real name is Shi Wang. I was born and raised in Taiwan, and I moved to the U.S. To study and then got a job. So I've been in the U.S. for more than 20 years. I really like to come to Thailand because when I flew out of Utah, the temperature there was -9 degrees and it was snowy, and I like warm weather here. So you cannot see a lot of me here in the near future. I prepared something today, but I think Ajahn Noi arranged the talk in a very excellent manner. I feel like my talk is an introduction to what the second talk you're gonna hear from Gister, because that's all about data. So I'm going to go on and try to condense my talk within an hour. I understand this at this time of the day, after lunch, everybody is tired. Myself, I guarantee you I'm more tired than you because the jet lag is still there. So with all the important people left, you have my permission to sleep. Okay, so let me see if I can play. Is it on? All right. Okay. The talks today, it's about climate extremes. And you guys must have heard climate change for a long time, or at least probably for the past 5 years, or if not 10. And today, I mean this year, the world has agreed to cut carbon emission to net zero, which is called net zero, to zero emissions in a foreseeable future. Whether or not we can accomplish this goal is questionable. It's up to all nations, all mankind to work on it. But the understanding is there that it's not possible to reach this consensus if people don't understand. So people understand climate change. What else do we have to learn? So I think the very important concept today is to learn about risk. Now I'm pasting here a quite recent press release, news from last year, only barely a year ago. And it is from the New York SEC, which controls the stock markets, that proposed that all the rules to enhance and standardize, basically to regulate climate-related disclosures for investors from companies. So this is very important news. This is not the first thing that's done in the world. I mean, European countries have been doing this for a long time. But all of you know, the New York Stock Exchange still is the world's #1 trading place. So the fact that the US finally is embracing climate risk disclosure means that all companies, big and small, as long as you go public, you have to disclose your climate risk to your company, whatever businesses you are in, all sectors. So that changed the game because now everybody needs to know financial risk related to climate extremes and climate change. And companies are scrambling to find data. That's a very important thing. That's something we don't have. So when it comes to climate extremes, we know that we need data to do that, global data. Okay? And it's just not one place because you have to understand not only your factory or your farm, but also your supply chain, and also where your product will go to. Okay, and then all the materials they use to build your buildings all come from different places, or those are composed of the supply chain issues then they can all be under climate risk. All this needs to be disclosed and calculated for your investors. So today, if you graduate, for students, if you graduate and work for certain companies in the future, or if you want to open any company, you need to know about this. And data is important. And it's not only about the distant future, like the end of the century, but also about next month, next growing season, next 2 years, next decade. So we have to understand prediction as well, right? So calculating risk requires data. Where would you get the data? Again, more details about Thailand's data will come from the second talk. And so right now, I'm really just to give you some introduction about why do we need to still understand risk. Now, if we already understand risks, you wouldn't be seeing this recent news about extreme events. Today, whenever there's a wildfire, heat wave, flood, reporters still flood in and ask this one question: is it related to climate change? Are we going to see this in the future? Okay. Myself, because of what I do for research, I was constantly interviewed by news. This is just one of the example.
Harsh heat wave is expected to start sweeping through India and Pakistan today.
This is Singapore's national news.
The professor of climate dynamics at Utah State University.
And that's me.
Heat waves have
so
always occurred. But
you don't need to understand what they're talking about. It's basically asking, is this climate change? What we're gonna do?
The range of
right? And then I start to say something.
We know that.
Right. So let's go fast forward. We don't need to hear me out there. But one thing that media constantly will fail to interpret, which might lead to the failed interpretation, wrong interpretation of the climate risk, is the probability. I want to take this example here. Now you see that the news says a hypothetical weather forecast for 2050 is already coming true. Is that right? Is that the right way? Now the truth is not. When they forecast something about heat wave, this is for UK, right? And they felt that people tend to look at the average line. They forget or they don't know how to interpret the range. So if you look at this figure here, what's predicted for 2050 was the mean. In fact, the range for United Kingdom to experience a heat wave like what happened last year has already happened. We are already in the zone, okay? So if your company or if your industry or if your government concerns anything about heat-related damage to human, to mankind, to labor, to constructions, well, you have to calculate that risk. Then you have to budget those risks into your financial report and for your company report for the investors. And people actually don't know how to do with that yet. So it creates quite a bit of information need and also market. If you know how to capture this opportunity, you can make a lot of money. So I prepared something that is actually prepared for the 6-hour lecture. A lot of topics, but I already get rid of a lot of details, but I cannot remove any one of them because I feel like they build on top of each other. So I'm going to try my best to talk all about this so you understand why this risk is important, okay? The basic of climate science comes into these complicated figures. You don't need to understand what's inside. I will explain, all right? I just want you to see some color pictures so you don't fall asleep. All this is about radiation. The fact that we have an Earth's climate that is warming more and more every day, and that is about climate greenhouse gas, is because radiation. The things that we human to generate energy from emitted into the atmosphere, and they cause the temperature to go up because the radiation budget has been shifted, and that heat is being trapped, okay? And there has been many good educational materials, including this one. If you're interested, you can scan the QR code to watch the video. It is like 6 minutes long, but I think it's a very good one to provide you the basic concept about why a single change in the atmospheric composition can change the worldwide weather. And the key word comes into this single word called equilibrium. Right? It's the balanced state. It's really like your bank account, right? If you overspend, then you run out of money. If you underspend, then you end up saving some money. That simple. So all the chemistry, all the physics about Earth's climate comes into this equilibrium. Now, the way that human beings has been working on generate the energy, and energy propels our wealth, has changed the equilibrium, making the world to warm up more and more. And the warming will affect the Earth's circulation, then the circulation will change its weather. And if they change weather, it will change the way that we experience our climate in the past. While we feel like it's been normal or we got used to, it's not been the same. Okay, and the change can be profound but small scale as well. That's why we need data. So the concept to really do this, if you want to get a degree, like Ajahn Paricha, who spent years in Utah getting her PhD degree, is to understand some physics like this. The Earth's weather is really like water, and then it takes a fluid dynamics concept to understand and then to simulate those things so that we can forecast the future. In the past, the Earth's climate has also changed. We came into ice ages, out of ice ages, because of these orbital changes. They call the Milankovitch cycles. That's because the Earth changes orbit around the sun, and also the tilt and all that. It takes a very long time, but then it forms a periodic shift, and it changes the distance from the sun. So the distance changes from the sun, changes the radiation budget. So we come back to the very important concept of radiation. That is how the radiation change, as you see from the black figure, can change Earth's climate, like a temperature from the right figure there. Okay, so we come out of Earth ice age into ice age in an interglacial period, ice age like that in the future. The problem is that with the human-caused global warming, we are pushing the Earth's temperature towards new highs. And not only that, all this change happens in a very short time compared to this naturally occurring climate change in the past. So no one has really seen this happen before. We don't really know such a drastic change would do to the weather, even though we have started to experience climate extreme events worldwide. Okay. Now, so I want to introduce you some factors that can affect Earth's temperature, such as volcanoes. Every time there's a big volcanic eruption, because of the ashes that erupt, that it block the sunlight, it causes the Earth's temperature to go down, actually. But then you fall back up. This is called natural variability. There's nothing you can do about it. And this process, the materials is called aerosols. It's basically tiny particles in the air. If you don't know what aerosol is, turn around and look outside the sky in Bangkok. That is called aerosol. Okay, it blocks the sun and block the radiation. Now, we know that aerosol not only has something to do with, can affect radiation, it affects our lung directly. And then the two combined can make a huge difference in climate as well. Now, I'm starting to introduce some concept that I have personally researched for. So this study came from my own research, which focused on northern India, which is one of the world's most polluted regions. Okay, because of all these human activities that they just don't see that they're gonna change in the near future or ever. Okay, so from satellite observations, you can see that the aerosol concentration has built up, continuously. They went through the up and downs, but over time they are building up, and with that, it has dramatic consequence. This is one picture I took when flying from New Delhi to Kathmandu in Nepal. I look outside the window and I see this. I can see the Himalayas and you see the aerosol depths. Now, this aerosol is very deep in northern India, very deep. That is very different from anywhere around the world, including in Bangkok here. Why? Because most of the time, our pollution is not that deep. The air pollution is shallow. For example, like Salt Lake City, Utah, it's about 300 meters. In South America, it's about the same thing. In Thailand, it will be about the same thing as well. Maybe 300 meter to 500 meter depth. That's called boundary there. It doesn't go that high. But in northern India, you can see that the high of the pollution level is almost 5 kilometer depths. So it traps a lot of air pollution inside. So, and over time, it changed the atmospheric structure. All right, it absorbs the sunlight, so you make the middle air hotter. But then you block the sun, right? So it makes the surface layer cooler. Now, when you have a warming mid-air and a cooling surface air, it forms stability. The air becomes stable, and the stable air will trap more pollution. And with the warming, it will trap more pollution. So not only did aerosols change the climate, it also increase its own aerosol compositions. It's a compounding effect, right? And then we all just went through COVID, and that's a natural experiment. Well, actually not natural, it's human, but it's an unintended consequence for pollution level change. Now, we all know that during COVID, especially in 2021, 2020 through 2021, all the government lockdowns, the society lockdowns, travel bans, it dramatically dropped the aerosol level. The air becomes cleaner. You know, people in India, in northern India, they claim to have seen the Himalayas for the first time in 40 years. But that has consequence too. Now, in 2019 and 2020, during the Bay of Bengal tropical cyclone seasons, there were 2 super cyclones. One is called Fani, one is called Amphan. And then these 2 were record-breaking cyclones. In 2019, Cyclone Fani broke many records. And we started it and realized that the warming ocean and warming air has made Cyclone Fani to be stronger. But aerosol actually pulled it down. But in 2020, without aerosols or with a reduced level of aerosols, the warming and the reduction of aerosols actually made another cyclone that is stronger than Fani, that's Amphan. So that broke a lot of records, and it caused a lot of damage when they make landfall. So the concept goes like this. Over the past 30 years, you have warming to intensify any cyclone developed during that time. But the aerosol is weakening it. So without warming, aerosol effect, such as in 2020, you have you don't have the force to pull it back. The cyclone becomes more intense. So we can say that we almost have this love-hate or bittersweet relationship with aerosols, and when it comes to severe weather. All right. Now let's move on to extreme events. Why are they dangerous? I want, sometimes I get a lot of questions, not only from the reporters, but also from students, like why would a warming climate induce extreme weather that are opposite? For example, drought will become stronger, but flooding also becomes stronger. Even cold weather will become stronger. It's like, hey, why are this happening all the time? Well, I can explain that. If you look at why severe weather happens, it only comes down to 3 elements: instability, moisture, and lift. Now, if any one of you would walk out today to remember anything, I hope you will remember these 3: instability, moisture, and lift. So let me use one example to explain this too. Now, I'm using not storms, but fire. And I record this video myself from my home in Salt Lake City, Utah, looking west. There was a summertime wildfire event. This was not a super big wildfire, but still they burned many hours. Now you are looking at smoke, and on top of the smoke, you're also looking at clouds, right? So then I want to use this fire to explain why storms form. Now the first ingredient is instability. Within those plumes, it's very unstable because it's burning, right? But outside, the reason you see blue sky And the reason you see the clear sky is because it's very stable. You don't see clouds anywhere else, only under the fire, right? That's when instability will cause. Now you start to see clouds on top of the smoke. Now that's supposed to be very dry day. That's why there's a fire. But however dry, no matter how dry the air is, it still contains moisture. And then when the moisture gets lifted up, it condensates and becomes clouds. So this is an example to let you see that even though our eyes cannot see water, moisture in the air, through this process, you can see that there are water in the air. So they can form storms. Now the third element is lift. Lift is a mechanical source. Usually it came from frontal passage, but in that event, it was by fire. Now, if you apply these three concepts into clouds or storm in a moist day, in the summertime, afternoon, you're going to grow a lot of clouds. I think last rainy season I was here, I experienced a few of the big thunderstorms here, and then I witnessed the power of monsoon in Thailand. It's about the same. So then you got something called atmospheric waves. That is gesturing how they form, how they propagate, and then they can interfere this instability, moisture, and lift. So they can cause severe storms, severe weather as well. And that is why when we have a warming climate, when climate warms up, we got this almost opposite swing of the weather patterns. Dry, drought, heat wave, and then flooding and cold storms like that, okay? So when it comes to mathematical expressions, it comes to this simple equation that the warmer the air is, the more moisture, water it holds. So which means that when it doesn't rain, you get more moisture from the ground, which makes the ground drier. That's why it causes drought. But when it starts to rain, because of the lift, instability, then it rains more because now you get more water in the air. That's simple, very simple, okay? All right, so I'm going to speed up on this. So as a meteorologist, as a weatherman, we constantly track all these elements in terms of data to predict storms. And that is also the reason dry gets dry, why dry gets drier and wet gets wetter. And then when all this happening together, you have something called a compound extremes. I'm going to use this 2018 example that happens in Japan as to explain why. So in July, Japan, within only 7 or 8 days, went through severe, devastating flooding, and then after the week, heat wave. Now that they happen almost like a back-to-back, and there's two different extreme events. Now it caused a lot of damage because the flood water has really not receded yet, and then the heat wave came in, and it really prevent all those rescue and reconstruction workers to work, and then that led to more damage, more casualties. And we conduct a research on that and realize that this can be explained by the whole system. And that's why I'm here to explain, to represent a more like a larger scale global climate person to understand why these things happen, okay? So I produced this cartoon just to let you understand what our monsoon system looks like. In Thailand, you may not experience something like that, but in East Asia, where I grew up in Taiwan included, we will go through this monsoon onset process. In Japan, it's called Baoyu phase. Now, if you look at the place where Japan is, and then associated with the front is the subtropical high pressure. And then we also got tropical monsoon circulations that provide a lot of moisture. Now, this forms the basic circulation, and then also Southeastern monsoon low pressure systems. All these combined, it forms these complicated monsoon circulations. But then they moved. They are not the same every year. They move. Okay, in 2018, we have also the jet stream that becomes very wavy. It provides a lot of lift. And then we have a typhoon. So all this combined make the flooding in Japan that was unprecedented. And then this monsoon will change over time. Just like in Thailand, you get the monsoon phase, rainy season, cool season, not really very cool, drier season, rainy season again. The season changes, and so is for the Japanese monsoon. In 2018, all this circulation amplified, right? So the amplification makes the high pressure in the subtropical high pressure stronger. That traps a lot more heat. And the heat makes this heat wave that kills a lot of people. The heat wave ends up killing more people, especially the elderly people, than the flood did. It's very counterintuitive. Okay. And then there's a revival phase, which means the rain comes back. Now this time, this is late summer, so this time the rain usually came with the form of typhoons or tropical cyclones. And in 2018, this typhoon wiped through Osaka airport, flooded the airport there, and damaged a lot of planes. So under the warming climate, we have everything intensified. The trough intensified, the subtropical high, the high pressure intensified, the jet stream intensified, and it makes this combination or the sequence of extreme events to happen more frequently. So increasing the odds or the possibility for the compound extreme events. Okay? So when they move, you're going to see patterns like this. The Japanese monsoon goes like a wet, dry, wet, and then this will amplify as well, which means flood, heat wave, and flood again in the future. Not every year, but more and more likely in the future. So this is how you understand the process and then start to consider risk and how you can quantify the risk. The same thing for Taiwan. And then now let's look at cities. I'm using this example from Taipei because also the big city, but Taipei has more complicated geography than Thailand, than Bangkok. Bangkok is more like a flat land, but in Taipei, it's surrounded by mountains. It traps the heat. Now you may have all heard about the urban heat island effect. In Taipei, it's more like a heating pan, okay? And it goes like this. Every day in the morning, sunrise, and then you start to have sea breeze. And with the urban heat, it generates heat, and then you start to produce thunderstorms, just like in rainy season in Bangkok. And then it cools down the air, intensify the land breeze, which, by the way, carry out the pollutions, so that it's not so bad, right? And that's the process, and then repeats every day. But over time, we found that the thunderstorm activity has increased. The thunderstorm intensity also have increased. Now that will create problems, especially in urban areas. I have experienced how much worse the flooding in Bangkok can be during monsoon time. And then can you imagine that if the frequency increases, the life is going to be miserable. Occasionally, some people will get killed because of that. I'll just go on for that because those are the details. When it's too hot, we like it to rain because it cools down. But too much rain causes problems. In the city of Taipei, the city maximum capacity for drainage system is 73 millimeter per hour. It's how the engineer designs the drainage capacity. But then the 73 millimeter per hour was based upon data 50 years ago. Today, it's very easy to have a rain rate over 100 millimeter per hour. So it's guaranteed to cause flooding because every time it happens, it exceeds the construction or the drainage limit, right? If they don't change that, the city is going to be flooded every time it rains, just like what I experienced in Bangkok as well. And then the next question is how long will we see this change? Will it go unstoppable or it gonna level off at a certain point? Now, this is something about climate prediction and projections that my area of research has propelled me to do. Now, I checked the Bangkok's heat island literature. I found a lot of remote sensing studies about the heat island. I've really not seen too much about the weather impact in climate change. So I think that if anyone is interested in doing this research, I'm very happy to collaborate. So move on. Another example for compound extreme events is this paper lead authored by Arjun Palicha, and it's about the 2011 Great Flood. Now, I'm not showing the analysis, but just the conclusion that it's another example about what make a compound extremes, right? From anything from a cooler, a wetter than normal pre-monsoon to the active monsoon, and also with sea level rising, and also with global warming that increase this frequency of flood to happen, and the intensity of that. Of course, there will be man-made issues like the dam control, water management. So this is something we found, I feel like it's very important, but very difficult to quantify about compound extreme event or compound extreme risk. So let's move on more. Next, let's talk about something not so intuitive, a more indirect process. One of the most profound example is wildfire. Now let's see if we can run this video. If not, it's okay.
This is a crisis. If we were on a plane, I think the pilot's control
Let's just play it for
would have
2 minutes and we'll move on.
Siberia, USA, Turkey and Greece and Italy and Portugal in recent years. Huge areas just going up in flames, everything being reduced to ash, scene after scene of hillsides ablaze.
I'm playing this because the reporter provided a very simple
Wildfires,
explanation.
in one sense, very, very simple. It just needs a spark in dry conditions to set them off. But in another sense, they're also very complex because the extent to which they spread depends very much on conditions in the ecosystem. How much moisture is there in the ground, in the air? How long has it been since there was last rainfall? What kind of trees there are? How dense is the biodiversity? Fires tend to burn faster when they're in a plantation and there's just one type of tree. There isn't much undergrowth, moss and things like that that can absorb water. You get what scientists are always describing as tinderbox-like.
It's like it's not very easy to understand, but I will just fast forward. It contains a lot of things from ecosystem, weather, climate, and the management, basically, right? And so the first line of climate control is natural. It's not really about human being or climate change. It's about natural variability. I used to write for the US government for their blogs, and then this is one of the posting I wrote about how El Nino affect wildfire in Southern California. Now you're seeing this picture as a fire burn mark from very old trees. Now against common sense that trees don't necessarily die in a forest fire. A lot of them survive. And then with their age, they record many different historical fire events. Now with the tree ring, which changes every year, you can really date what year all those fire happened. Then you can trace it back to climate events. Now, I have marked or count about 5 out of 6 fire years to be with La Nina events, which is a massive cooling of Pacific Ocean. And that contribute to drought in Southern California. And then you can see that this is a climate-driven events. They come and go. So it goes like this. Precipitation variability or climate comes like that, right? You have this El Nino and La Nina, the Pacific Ocean changes that takes multiple years to happen. Usually it's there, but it's not so clear. Sometimes it affects the climate, sometimes it doesn't. But as the climate warms with global warming, we know that this kind of variability will increase. The effect can be reflected by this drought index in California. This is the fire-related drought index. Now you can see that in the later phase of time, you get more synchronized variability of fire-producing climate. And the net result is that this is a fire count. So the fire not only increase, they increase by following this reason as well. So next time there's a La Nina event, the fire might burn more because of the combination of all these changes, right? And then in 2015, we published this paper. That was the very first time we were able to use just one big global climate model that has the land process, the vegetations, and they can directly compute fire risk from one model without having to plug in the ecological model, vegetation model, fire model. It came out from one model. That's important because then we can understand and trace back how the ocean variability and climate change and human-made global warming could and affect fire behavior. Now you can see that without global warming, it's the blue line, it's flat. The trend is flat. With global warming, the fire risk will increase in the future. But the more important thing is here, you look at the black line. That's the observation of extreme fire danger. So you see that the model under predicts what the fire danger would be. So that's profound impact because with the modern tool, we're still not being able to grasp the full extent of such a risk. Now let's shift to Taiwan. Like Thailand, we are all in this humid subtropical monsoon climate. Usually, large-scale fire is not something that we care. But during the past few decades, the island of Taiwan has seen more and more widespread wildfires. Okay. Not to the extent of Western US or Australia, but still consider the size, it's bad. Now, I use this satellite derived groundwater index from the twin satellite called GRACE from NASA. Now you can see that it spends a little bit more than 2 years on the shallow groundwater effect. The thin line is soil moisture. So you see the soil moisture goes up, but sometimes the groundwater doesn't follow, like in the later period of time. So the later period of time was the most intense drought ever recorded in Taiwan. That happened during 2020 and 2021. Now, in the later part, you can see that if the groundwater depletes to a certain level because of drought, it's going to produce something called sponge effect. In that, you see the soil moisture comes up, which means precipitation, but then it came down, and the groundwater doesn't really change. Which is bad, because then the root of the forest cannot absorb the water. Then the whole forest become unhealthy. As seen from this satellite-derived green, this GCI index there, you can see vegetation health. Now, the trees and forests respond to climate or drought with a delayed process. So it took about a year or 9 months for the entire forest to respond to this drought. When river already is dry, tree was still healthy until later part. So in April 2021, you see most of Taiwan has this red color. Most of this forest has this red color, meaning that the trees were stressed, unhealthy, which make them easier to burn. And then in May, there was a huge fire, a record fire happened in the middle of the forest. And that caused a lot of damage. So, and that's the process I explained. Okay. So then, this is something, it doesn't take just one conclusion. It takes multiple elements and you link them up and then to reflect or predict what might happen for.
Oh, let me get the Weather Bureau here. We've sent the weather. James, you there?
Next thing is.
Yeah, this is another James. This is Jim Fiddler in the Weather Bureau.
This is
right. Right in there. What about some temperatures, Jim?
Weather forest, weather surface to get in.
How do you know what the weather is going to be like so you can plan ahead? While you're busy with your everyday life, a global network of gadgets scan and measure the atmosphere, collecting data from all over the world. Radar systems, weather balloons, ocean monitoring buoys, and lots of other cool instruments track changes to help predict the weather. Another vital ingredient is space. Way out in orbit, weather satellites are getting the big picture of atmospheric changes. Give us the ability to see the weather before it reaches us.
Because of the time change, I will speed up. You're going to hear a lot about environmental satellite data from the next talk, but the video was telling you about weather satellites. Weather satellite means that the satellites that measures clouds, moisture, rainfall, in addition to environmental satellites that monitor everything on the surface. And then all this data morph into weather models, computer models, and then produce the weather forecast that you can simply ask your phone to see. If you want to fly to Chiang Mai today, you want to see the weather for the next 3 days, it's very easy. What's the weather in Chiang Mai? It's gonna tell you. So all those information are easily accessible, but they are all produced by computer models based upon true data, if you know how. But how do you know how? Well, personally, I opened a class in at Utah State like this. It used to be designed for graduate students, but then more and more undergraduate students needed. So I have to tone it down and restructure and teach it for undergraduate students. I'm thinking about teaching it for more general audience because the tools are getting better and the data are getting more important and more accessible. So things have to change. It's just one example, one simple example, how you can do it. Okay, sorry. This time is up. Right? Yeah, we just talked about weather. Now, the weather models are now so good that government agencies can run them for a long time. There's something called decadal, which means 10 years climate prediction. Decadal prediction is very important because it fits the politician's life cycle. Think about that. If you are your government elected officials, your turn, let's just say 2 years. That's roughly about 8 years lifetime. Anything you cannot make a decision for has the ability or has the lifespan for about 10 years to see the effect. And if when you need information for climate, like carbon, like anything else, then you need decadal prediction. It's getting better and better these days if you know how to access them. And one example is what I did for the research is for the Colorado River. Now you see where is this place? Las Vegas. And do you know where it is? It's in the middle of the desert. Okay, but then you see this lush city with abundant water and electricity because of the Colorado River. Now the Colorado River is drying, as you can see from this chart, and the blue line tells you the Colorado River water supply, basically the river flow. The red line is the water demand. Now you can see the red line overshoots the blue line, which means it doesn't provide enough water for Southwest US, right? What do we do? Well, you need prediction. You also need to curb back the water's demand. You need to do this together. So we use the modern technology, the computer model and the decadal prediction tools to do this kind of prediction for the future. Each time we output about 5 years to 8 years of data, then we update it every year. Then that way we can help water managers to control how much water they can release, and then for city planners to see how much water restriction they have to implement, and then you save money on that as well. Now let's move on to the very last subject. How do we build tools to study all this region? This is the one video I took. You can download app. Now this is the app I have in my laptop. It's just called General Circulatory Model, GCM. It's a simplistic model. It can simulate the Earth's circulation, jet streams, storms, and then temperatures. Compared to the real world, this is the real world not long ago, okay? You can see that a simple model can produce something realistic. Now then you can use this model to simulate the Earth multiple times. The reason we need to do multiple times is because of this so-called butterfly effect. You do a very small change in the beginning, the outcome will be very different. So if you do enough simulations, you capture all the possibilities, and then you can understand what the signal is rather than noise. That's the basic concept for climate projections. Okay. Now think about this. All these changes like our mood. Today I can appear in front of you, I have the bad mood. Why? Maybe I have an argument with my wife, or maybe just no reason, I'm hungry. I have a bad mood. That's unpredictable. But my personality is kind of like fixed. Over time, even though I have these mood changes, if we are friends for 1 year, you kind of know who I am by personality. Climate change is like a personality change. Then the weather is like a mood that you just swing, you just change it unpredictably. Okay. Now, there's one important message I want to say in the end is climate data are mostly free. This is one example, one of the website you can use. I have instruct graduate students to use this rather than typing out computer coding by themselves. You can use a lot of that to help you to get data. And there are also companies that start to produce climate risk data in terms of a price tag. This is an example from the weather service company that was bought by, I forget which big funds. They got really rich because they instead of showing temperature, precipitation, sunshine for the future, they put out money or disaster or dollar lost for the future, tailored to your business. Now, this is something I think the founder was an MBA from Columbia, and then when they learned about this, they launched this startup company, hiring some programmers, and then apply these financial models into climate model data, produce something like that. After a few years, the S&P 500 funds just bought them out. So they made a lot of money on that. And this is a trend. They don't provide all solutions. So you still have your chance if you know how to access and interpret climate data. So this is my very last slide. It's a summary. First of all, compound extremes are most dangerous. Not just flooding, not just heat wave, but when they happen together. And we are seeing more and more of such events. And it's very unpredictable. Okay. The second thing is that sometimes very cold weather happens, and then it can caught you by surprise. The reason is that even though global warming is happening, the Arctic is still very cold. So occasionally, with the Mandarin jet stream changes, Arctic air will intrude middle latitude or even subtropics, making cold extremes. I make an example. Back in 2020, Taiwan at the time had only 7 people die from COVID. But then in January, there was a cold surge came in, and then within 2 days, 200 people died just from the cold event. Heart attack or breathing or hypothermia, they just die from weather events when COVID only killed 7 people. Insurance costs can drive up inflation. That's compounding. Now, in the Western US, when a lot of homes and communities were lost to wildfire, insurance company increased their cost, right? And the cost is actually shared not only by Western US or California people, but East Coast people as well. Everybody's insurance went up because insurance company have to cover their loss. And then the only way you can get more knowledge and more information is to build tools. And for that, you need data. So in the end, I want to say that climate data is accessible. I am here and I will be here many times in the future. I want to collaborate with all the experts to build useful data to cope with climate risk. Thank you for your attention.
Thank you very much for very interesting presentations from Professor Simon Wang. So actually that is very interesting to give us about the basic knowledge or basic science on climate extreme. And I think that after the presentation, we can discuss more what exactly climate extreme. And actually what I capture is that if we know the climate extreme, we're gonna know risk. If we can predict risk, it's gonna make us have a better life, something like that. So let's move on for one more very interesting topic too, about the climate change issue, the extreme weather events and major impacts on agriculture and natural physical environments. So I think this is a very, very challenging topic for these time periods and also by the future. So please welcome for Dr. Pakorn Phet-Prayun, the Director from Geoinformatic Innovation, GISTA. We give the stage for Dr. Prayun, please.
Thank you very much, Dr. Parishar. So, good afternoon, all of you. So, I look around from this room and I feel like I have more energy because I saw a lot of young people. That means young people have more energy and have more time to work a good thing for our country and our lovely planet. And now we're talking about climate change. Climate change, now I think we are lucky because we are the first generation who know the climate change. Right? We are the first generation who know the climate change. And we are the only one generation to fix it because no time for the next generation to fix it because it's too late. And now that's why I feel I have gained more energy. One, I got new knowledge from Professor Simon. Yeah, I learned a lot of things from you. Thank you very much. Very, very interesting and nice presentation. And 1 hour is very meaningful for me to learn from you. Thank you very much, Professor. And also, from now, I will spend about 15 minutes to share some of my knowledge and my experience regarding to the remote sensing, that study about climate change, study about agriculture, and how can we get the data from space and then monitor the effect of climate change to the agriculture activity or agriculture in this area. So I'm from GISDA. So GISDA is the Space Organization or Geoinformatic Organization for Thailand, the Remote Sensing Center of Thailand, GIS Center of Thailand. So everything that relates to the area observed by the satellite or analyze the spatial data, this is related to our office. So
2, 1, 0.
Oh, it's too fast. So now I will bring you to the space. But please go back to the previous slide. So this is my outline. You will see a lot of things that I would like to transfer my experience and my knowledge to you. But first of all, I will introduce some of my works, my experience, and then we'll give you some idea of the impact of climate change. We're gonna talk about the extreme event and slow onset. The impact of the climate change have two phenomena. One, slow onset, right? Like a sea level rise, melting ice sheets, the temperature rising. This is slow onset. So it will take time to increase the temperature. Will take time to increase the water level. And another one is extreme event, like when we have the experience with the heavy rainfall, very severe drought, a lot of flood during the rainy season, dry spell during the rainy season, and during the agriculture cultivate season. So this is the problem of the extreme event. We were talking about the slow onset and extreme event. Sometimes slow and onset and extreme event relate to each other. Extreme event impact very short but very severe, very serious. But the effect is takes long lasting, takes long period for the slow onset. This is the meaning of the impact of the climate change. And then focusing on the extreme event with flood and drought that we have experienced, we face with every year or the year. Then we move to agriculture systematic monitoring. What the effect of flood and drought affect to the agriculture activity. And then if we have time, we will be talking about, so we know the climate change, and how can we cope with it? And how can we adjust for those changes? So we will be talking about the climate resilient agriculture. And then lastly, if we have 5 more minutes time we will talking about the carbon credit, which is a hot issue for now, and then we're talking, and also particularly carbon credit for the agriculture area, not for the all for forest area. Here all of the my topic that we will talk today. Here's in my organization.
Zero and lift off Space Shuttle and Lights.
In the 21st century, the age of the space economy is rapidly growing. Space is no longer for only the government's projects. But the ever-advancing technology has inspired the private sector as a key potential of the space technology race of each country. Space is the treasure trove of knowledge and cutting-edge technology and the resources of tomorrow. Numerous countries push their resources towards space economy to harvest space for the benefits of the countries and their people. Space and Technology Development Agency, public organization, or GISTA, under the Ministry of Higher Education, Science, Research and Innovation, is a representative of the Government Space Agency of Thailand, which has been continuously developing infrastructure and human resources for the space industry. In order to make Thailand as the leader of space technology in ASEAN, and to ultimately be the key importance of the space industry of Asia and the world. Over the past 2 decades, GISTA has been utilizing space and geoinformatics technology to support the development of Thailand in various areas, especially in the 6 key areas of cartography, agriculture, water resources, disasters, urban planning, and natural resources. With the geoinformation derived from THEOS, Thailand's first ever observation satellites and international satellite networks, to upgrade the entire space technology ecosystem of Thailand. Recently, Thai researchers and engineers have been studying and developing our geoinformatics intelligence. Under THEOS-2, which includes 2 satellites, main and small satellites, terrestrial satellite systems, satellite testing and assembly center, and the development of geoinformatics applications and solutions, and Actionable Intelligence Policy System, or AIP, with the goals of using advanced geoinformation as necessary in policy decision-making. Today, Thailand is not only a technology buyer, but we are also capable of learning, manufacturing, and creating innovations for both internal and external services. The development of human resources by enhancing the potentials of space and geoinformatics technology will create knowledge and keep the sustainable growth of Thailand's space technology. GISTA is proud to be the key supporter of Thailand's space industry evolution. Our goal is to support all collaborations between the government, the private, the education, and civil sectors for the potentials of our talented people and the space industry, and to create opportunities for Thailand's space economy growth. GISTA has been preparing for the 21st century, the dawn of the golden age of humanity's space industry. we will move forward as the innovator of space technology. Alongside Thailand's space industry entrepreneurs, to mark Thailand's success in the exciting age of space exploration. At the frontier of the ever-expanding knowledge in space and geoinformatics technology.
So this is my office, and you know the word that geoinformatics, right? Geoinformatics includes three technology. One, satellite remote sensing technology. Another one, GPS. And the last one is GIS. So we use these three technology combined to geoinformatics. It's the name of our office, GISDA. I hope anyone knows this name. So, and I hope I will see some of you in GISDA after you graduate. So you will be the new worker or new staff of GISDA if you're interested. So we need the new generation. So for me, it seems to me I'm getting old. So I think we need a new generation to help us to improve our technology, our work, and so also our country. Here is the satellite. You will see GISDA used mainly two satellites. One is the Earth observation satellite, and another one, the weather satellite. Weather satellite is like a geostationary satellite that is far away from the Earth's surface. It's about 36,000 kilometers. 36,000 kilometers. If you can see the satellite, you will see the satellite like a not moving, like a station, and looking at the same location at the same time. So they will capture the data for 24 hours and update the data to us for every 15 minutes. For example, the Himawari satellite, as Professor Simon says, you will get the data for every 15 minutes. Get the data. You will see the cloud movement. You will see the type information, or you can see the movement of the atmosphere. And also for the Earth observation satellite that I call near polar orbit. This one is the low orbit satellite. So it's high about 500 to 1,000 kilometers above the Earth's surface. That means it's far away about from Chiang Mai to Bangkok or Bangkok to Chiang Mai and capture the data. When you're looking at the data from Google Earth, you're looking from the Google Map. So this kind of satellite that provide the data for Google Map. So you will see a lot of data, a lot of satellite data orbit around the Earth. And we use this data to monitor the thing over the Earth surface and also atmospheric profile. So we monitor for the Earth surface for the biosphere. We monitor snow and ice, cryosphere. We monitor water movement, water resource for the hydrosphere. And also we monitor some like PM2.5, some particle from in the atmosphere. So all of the sphere, we can observe it from satellite. And Thailand will launch the new satellite by the end of this year. Probably by September, we will launch the satellite, very high resolution satellite. With the resolution is about 50 centimeter. 50 centimeter, that means everything that bigger than 50 centimeter, the satellite can see it, can observe it, and can capture the data. So that means the satellite can see, we can see the car, table, or even your chair. If you put in the football field, so we can see the chair. So really high resolution one. So we use all of these satellites to monitor and to study about climate change. And also we can get the data for every resolution or every scale. So we can monitor we can see how movement, how change of this area, land use, land cover change, and also we can measure it. We can measure how big of it, how hot it, what is the temperature. So we can measure it. And then finally, then for sure, we can make a map. we can make the report from this satellite. And then, like Professor Simon said, we can model it. Use the satellite data to input the model, and then we can model, we can forecast it. And then we have for monitoring, measuring, mapping, and modeling. All of these 4 M will useless if we cannot manage it. We observe the data, monitor, measure it, make a map it, model it, in order to serve for the manage. So if we can manage it, we can improve it, or we can solve the problem. This is the good thing for 5M. So the role of the remote sensing satellite, we can provide the data for the different scale, from the global scale to regional scale or local scale. And here is the area of the thing that we can do for all the application that you already seen in the video. And now we will move to the impact of the climate change. As we said, slow onset or extreme event. You will see there are a lot of slow onset that we know from the climate change, like a sea level rise. We see the loss of the biodiversity. We see green ice sheet melt. We see sea level rise, increasing temperature. For example, this is a slow onset. But for today, I will focusing on the, you will see the red dot or the red circle. This one is the extreme event. For example, we will talking about flood and drought. And also we talking about typhoon for a little bit, because the phenomena is linked together. And also when we talking about the phenomena, when we talking about climate change, we're talking about the effect of climate change. So every problem, every phenomena, we have to study in the holistic picture. So one factor, one parameter change will affect to another factor. So that's why when we study about temperature, we have to study about other things like a precipitation, pollution. We think temperature, not only surface temperature, we have to thinking about water temperature, water vapor. We have to talking about the cloud formation. We have to talking about the biosphere, how state of the paddy field, how state of the vegetation, for example, because all of the parameters relate to each other. So if one parameter have some effect, or increase or decrease, will affect to other parameters. That means we have to study for all the parameters that relate to the topic that we want to study. If we want to study climate change, we have to study for all the parameters. And if we want to study about agriculture, we have to study for all parameters that relate to your field for the agriculture or crop area. Not just only for the NDVI or the vegetation index, but you have to thinking about how to measure the weather, how to measure the surface temperature, how to measure the precipitation, so from the satellite. And then you will understand the phenomena. This all the data remote sensing can provide you. All the satellite data can explain and give you the data.
Our planet is the setting for dazzling and interconnected webs.
And this video will show you how relate for the other parameter.
Amazing to behold from close up and hypnotic when seen from above. From space, the fleet of Earth-observing satellites operated by NASA and its partners illuminate the links between these systems. Temperatures on the planet affect all of them, which means each one is impacted by a warming climate. During 2020, global temperatures matched the warmest year we've measured, and we experienced the most active hurricane season ever recorded, with many storms quickly intensifying, likely as a result of warmer seas. Heat in the oceans is like fuel that powers these massive storms. But incredibly, dust swept up from northern Africa actually plays a critical role in the formation of hurricanes. It's also a key source of fertilization for the Amazon rainforest. Due to climate change, dust plumes are expected to decline, and then so will their impacts on vegetation and ocean away. Our satellites and field research allow us to pay close attention to the Amazon rainforest and other vegetation across the world, helping us track how fires, deforestation, and disasters affect the world's plant life. We can also study how those vegetation changes, in turn, impact air quality, waterways, and the climate. That same science helps the world's farmers boost productivity and deal with extreme weather, including drought, early freezes, and heavy spring rains. The observations can also help track some unwanted byproducts of food production. Fertilizers used in farming contain high amounts of nutrients to help crops grow, but those same nutrients can cause sometimes dangerous blooms of algae in waterways, which can affect local economies, recreation, fishing, and human health. They're often so large, they're easily viewed from space. Clean water and clean air are two cornerstones for maintaining healthy people and wildlife. Satellite data and NASA funding help map how animal migrations are affected by water sources, as well as light pollution and habitat loss, and also helps find solutions. The view from space is especially important in the Arctic and Antarctic, where animal habitats are rapidly changing due to climate change. And so is the ice itself, with Greenland and Antarctica losing enough ice in just 16 years to raise sea level by ½ an inch globally. We can also measure snow and ice farther from the poles, such as vital snowpacks in the Sierra Nevada and Rockies, and in the Himalayas, where rapidly draining glacial lakes can cause sudden and dangerous bursts of water downstream. Earth's climate is changing, and with it has come a new intensity to weather events and hazards that can lead to disasters, including floods, fires, hurricanes, and heat waves. As disasters become more frequent and intense, NASA will use its satellites and resources to study the effects of climate change on natural systems and to connect people to technology that can build a more resilient world.
Yes, it's how satellite can capture the data. So you will see a lot of data set that we can observe or we can capture from the Earth observation satellite. So now we move to the next. Oh, it's quite a little bit delayed. It may not.มันไม่ค่อยเคลื่อนนะครับ Okay. So for the just recap from the video that previous video. So for the parameter for the climate study climate change, the global climate observation system currently specific about 54 parameters that we need to know and we need to study and we have to understand for the climate change. So for more than 60% of these parameters can observe by the remote sensing satellite. So all the parameters, including the parameter from the upper atmosphere, lower atmosphere, to cryosphere, biosphere, hydrosphere, and lithosphere. All of these parameters relate together. And that I said, if one parameter change, will affect to another parameter and will affect to our life. So these satellites, some specific satellites, for example, you want to study about sea level rise, study with the TROPICS, Poseidon, or JSON, or altimetry satellite to make sure how high of the ocean surface. And also, if you want to study soil moisture, you want to study about radiation, you want to study about greenhouse gas, you can use other satellite to monitor it. And then this one is really good data source for you, because the satellite data, the good thing of the satellite data that you can capture the data almost near real time. And then you get the data for the whole area, your study area, because they capture the data for the wide area. But the more benefit that I like it, you can get the data from the history. That means you have the historical data that already recorded. This is a good thing for the satellite. And I like the historical data because if you want to know something and you cannot measure it in the past because you then don't have the time machine, you cannot get the data from the past, but satellite already recorded. So one thing that I forget to tell you guys, so my voice is very like a very low tone, you know, monotone and low tone. And you feel sleepy? Somebody feels sleepy? Yeah. And also I have very strong accent, So if you not understand, if I speak too slow and slur, you cannot catch me, please feel free to stop me and ask me again. Okay, sir? You can ask me anytime. So we have a lot of time for today. We can discuss and we can talk until dinner during the night. I'm happy to do that. Yeah, if you have time, yeah, I have time. And also, if you feel sleepy, feel free to go outside and then drink some coffee and break that I'm looking for, and then come back and then listen again. But if you feel sleepy again and you cannot withstand it, so please raise your hand. Raise your hand. I will decrease my voice. I will walk I will drop down my voice. Please slow down, and I will ask the technical guy to shut down my voice, and then we will sleep. Okay? Yeah. Please feel free to ask me, and spend for like 40 minutes from now, and gain knowledge and experience from me. Yeah, I'm willing to explain all of you. Okay, we will go to the next slide. We were talking about the slow onset, just one parameter about the ice sheet, about the melting ice surface. So this is because of the most effect from the global warming. When the global warming, the effect of the global warming, the high temperature, increasing temperature, the ice will I think, okay, now it work because I think this, the remote control in my hand is not cooperated with me. Here is the ice sheet, and the big ice sheet on the North Pole and South Pole. Ice sheet in Greenland and Antarctica. So you will see that there are decrease of the ice mass over time. This is many gigatons. So we use the satellite, great satellite, to monitor the gravity and to calculate the ice mass change. And we will see there are a lot of ice melt in Greenland and followed by Antarctica. And there are a lot of ice melt. I forgot how many gigatons, but it's a lot. It's about 1 year is about 6 times than the glacier in the Europe disappear. So that means a lot of ice melt over this area. So very huge ice in the Antarctica. The thickest area is about 5.7 kilometers. But the Greenland is flat. So there are a lot of ice melt during the winter. During the summer. During the summer, that means about July or August. A lot of ice melt in this area. And the warmer the color is the more accelerates ice melting. So you will see almost all the boundary of the Greenland melt a lot, and they lost a lot of ice mass. And also in some parts of the Antarctica, they have a lot of ice melt here. So this is the main problem that we concern about it. Every summer you will see the news show that, okay, many area, all the area cover of the Greenland, ice melting and the water run off to the sea. So this is the thing that we concern. But more thing that we concern is if the ice melt and completely flow to the sea, it's no problem. But you will see the lake in this area. The ice melt but not flow or run off to the sea surface, but still on the top of the ice surface. In the physics, for the physics, water absorbs the long wave energy. For example, when the energy comes from the sun part to the atmosphere, the long wave energy, like a near infrared, middle infrared, absorbed by water. Water just reflects the short wave energy, reflect blue and green energy, right? That's why we see blue and green in the water surface. We never seen the red color of water for the natural water. So they absorb red wavelength, near infrared wavelength, middle infrared. And when they absorb the wavelength, the energy keep in water and then warm up water, change the temperature, it's a sensible heat. Change the water of the temperature. When they change the change the temperature of water. Change the temperature of water. That means the water getting warm. And then when they getting warm, that means they have the capacity to make more ice melting, right? Make more ice. This is really, really concern for the scientists. And then when it's warm, when ice melt, a lot of ice melting in this area, water try to find a way to escape. And then they dig the hole, right? The water coming to the beneath area of the ice sheet, And here is my professor, who is Professor Conrad Stephen, who is the former of the series director, University of Colorado, and he studied about this. He had a station in Greenland, and he had a Swiss camp. He from Switzerland, and after he retired, he go back to Switzerland and work with some department of snow and forest of the Switzerland, and he was the director. And during his teaching in University Colorado, where I graduated for, he studied about this. And you will see the graduate student in the yellow shirt, blue shirt, and red shirt is my friend. One from Canada, one from the US student, and one from Switzerland. And they study about it by using a remote sensing data. And when he cheat me, this area is really dangerous one. Because if you fall, you cannot escape it. So it's just one-way ticket, you cannot come back. So it's a very dangerous one. And then he need a volunteer student, graduate student. If you want to study, you can apply for the master student or PhD student or the university, and then you can go to this field work. Yeah, we need a volunteer to study it. And here how they do it. This is the main problem of the Greenland ice sheet. You see, here is the lake, and here moorland. Moorland is a French language, our moorland. You will see, there we see some channel that the water from the ice move to underneath the ice sheet. And we worry that it will crack the ice sheet. If ice sheet crack, I try to accelerate but my mouth not cooperate with my brain. So if the ice sheet crack, amount of ice like 100 gigaton, and the ice thick is more than 1 kilometer fall to the ocean, and then the ocean or the sea surface will increase the level. The level will increase, and the big wave will occur, generate the big wave. That's why some people say, "Oh, be careful about the tsunami because of the ice sheet crack." This is the problem. So now we use remote sensing study about it. And here, I would like to pass this because now my professor, he passed away. He passed away 3 years ago because he fall in this area. He fall in the crack of the Greenland. And now his body is still in Greenland, and he passed away. And I was very shocked on that time, because he go to field work every summer, and then he had an accident and fall to the marine. And then his body is still there in the place that he loved. So I dedicate of my good thing today, dedicate the thing that I do the good thing for the student to him, because he is one of the best professor for me. He teach me remote sensing. He teach me how about the eye sheet. He taught me about the remote sensing. And then, I have the full license for the lifetime license for remote sensing software, because he gave me. And one of the remote sensing software developed from this center. Okay, now we know that, the slow onset, the melting ice sheet, the sea level rise. Now we will be talking about the topic that we want to emphasize, we want to focus for today. So we're talking about the climate change. Here, the climate change in the top, you will see, and then the weather. Climate change and weather is related together. Yeah. And climate change, the climate, we're talking about the thing that long time, take a long time, like a 20, 40 year, 30 year. But weather is like a present, so short time. And also climate, you cannot measure it, but weather you can measure it. If you want to know the temperature, just use the thermometer. If you want to know amount of precipitation, just bring the can and then measure how much of precipitation in that area. But for the remote sensing, so we used to study about land surface. And when we study the thing, we have to thinking about the area or spatial. And we have to thinking about the time, space and time. So everything when you study about the space, you're thinking about resolution. The resolution, the x-axis show you the resolution. When you want to study about water, when you want to study about agriculture, or when you want to study about the climate or weather, you have to thinking about how much resolution data that you would like to have, you want to have. So if you want to study a very detail, you want to study about the urban area, you have to have the very high spatial resolution. You want to see the individual house, you want to see the individual car, high spatial resolution. And also, if the thing or the target that you want to study, it change a lot, it change too much over time. That means you have to have the very frequent data, high frequency of the data. You need the data every hour, for example, to monitor the storm or monitor the cloud movement every half an hour, for example. But if you want to study about the geology, the rock doesn't change too much over time. So that means you no need to have the very high temporal resolution. So depend on the study area that you would like to work on it. But for the agriculture area, if you want to monitor the crop type, you want to differentiate between 3 types, the resolution is about 30 meters is okay. You can differentiate between paddy field, coir, rubber tree from the forest, and also if you want to monitor how much of to monitor the age of the vegetation. So every week, every 2 weeks is okay, or every month. So this for the temporal resolution. Here is the picture that will give you some idea of how to choose the data. But the most important thing that if you study about the agriculture, 30 meter resolution is okay. Update the data every month is okay, enough it's ample for us. But if something happens, like an emergency situation occur, like flood inundation, or water inundate your study area, your crop area, you need immediately data. You need the data very frequent, because in order to evaluate how loss, to evaluate the effect area by inundation, that means you need the data immediately, more frequently, to see and estimate the damage. So that's why when we study in the more normal way, every week okay, every month update data okay. But if the disaster occur or extreme event occur when flood is coming, you need the data immediately. That means you need data every day or every other day to see the flood movement, to see the effect of the flooded area, effect to your vegetation. I will pass this movie, so because
we're already feeling
because we were talking about the
intense heat waves,
of the
longer fire
climate
seasons,
change,
droughts, and floods.
With,
The impacts of a warmer
someone
planet are all
already
around
gave
us.
you that.
And as global
give you
temperatures
some idea.
continue to
I will
rise,
pass
we
this.
experience
I will pass this video. Yeah, and also we will go deeper a little bit for the climate change in agriculture. So when we talking about the climate change for agriculture, mostly we thinking about the pattern change of the precipitation. We thinking about the temperature. We thinking about the extreme heat, tropical storm, and also extreme precipitation and sea level rise. These all affect to the water supply and also to affect to the agricultural behavior. Particularly when we talking about the precipitation, we're thinking about the flood and drought. So, and also flood and drought will affect to the field crop area, and also will affect to the productivity of the your agriculture field, and also will affect to the food security. So this slide will show you, the graph will show you all of the effect from the climate change to agriculture activity. But from now, I will focusing on flood and drought. And also, according to the report of FAO, so a couple of years ago, they explained that. So the most damage from loss for the crop and livestock production is due to the flood and storm and also drought. That means a lot of effect from many things, extreme temperature from the crop pest and storm, earthquake, another thing that affect to the agriculture activity. But the most effect likely from the drought is almost like 35% with the flood and storm. That means all of these extreme events is more than half effect to agriculture. And here we will focus on the monsoon and storm in this region. And we already know that the problem in Thailand,
is a season
we have a problem with the upland
was first described over South
This is the
Asia.
truth that
You
we
see
have
the
to
clouds
concern.
blossoming here during the summer part of the monsoon. For centuries, people have known about it, but only recently have we received enough data from satellites to really describe what's going on.
What you can see here is moist air that has evaporated from the ocean coming across India and providing rainfall driving the monsoon season. The great thing about GPM is that it allows us to see precipitating systems as a whole, over land and oceans, and then as they transition from one boundary to the next.
All of this rainfall drives soil moisture over land. It's beneficial because it promotes the economic activity that people depend on, for example, agriculture. As well, it fills the rivers, which provides water for human activity and the natural environment, as well as transportation. If the rivers get too full, of course, it becomes flooding. At first, the floods you see here are fairly minor and broad scale, but then they concentrate in the few wiggly lines, which are the river basins, for example, in central eastern China.
In mountainous regions, when the ground becomes saturated due to heavy rains, it can lead to landslides. Landslides kill thousands of people every year and are primarily triggered by rainfall. They are especially common within the Himalayan region each monsoon season.
One really cool way to look at the monsoon is to do a split screen and look at the summer and the winter at the same time. In the summer, the wind is blowing onshore, bringing the moist, rain-laden air into the continent. In the wintertime, it blows off the continent.
Now, those winds are basically driven by temperature differences between the ocean and the land. And where the land is nice and warm, the air expands and it draws in the moist air from the ocean waters. But in the wintertime, it's very cold. the moisture then goes from the continent back into the oceans. Over the past 50 years or so, satellites have been used to measure precipitation all around our Earth. With that data set, we're able to understand that monsoons occur not only
from the satellite record for 40 years. Now we analyze the data. Sorry, it was in Thai, but I can explain. So we analyze the data for the year, and we will see how change, what the rainfall pattern change in Thailand. You will learn that, okay, when climate change, some area will have effect with very heavy rainfall. Some area will affect they will have the very late rainfall. This is the problem. So the variation of the rainfall in over the country is not homogeneous. So they have some spatial variability. So if we look closer, we will see that some area they have a lot of rainfall, the increase of rainfall. But for the overall in this picture, you will see for 40 years, there are kind of increasing rainfall for the past 4 decades. But when we look closer during the dry season in the past 10 years, we will see that some area have more rain, but some area have less rain, decrease of rainfall. Particularly in the northeastern part, like in Ubon or eastern part, Ubon, Nong Khai, Sisakhet, for example. Here is we have more severe drought in this area from the data record. And also, if we're looking at some area during the raining season, you will see in the Nong Khai, like a northern eastern. So you will see a lot of rainfall increasing in this area. But the opposite side, you will see late rainfall during the decreasing rainfall during the raining season in Kanchanaburi. Here you will see a lot of the spatial variability of the rainfall, both temporal and spatially. So that's why we need to understand that. We need to see what happened in particular area. We cannot manage for the whole country with the same policy or same scenario, but we need to monitor and we need to manage for particular province, because different province, different area, different time, they have the different phenomena. Here is the example that we have to thinking about, because climate change is the problem of the area and time. So you have to thinking about variation of time and space. So this is the example that I asked my colleague to analyze the data for me, and then they give me the data like yesterday, right before I came here, and I get the data and no time to translate to English. And I hopefully you understand. So you understand Thai, right? You can. Okay. Yeah. Thank you. So if not, okay. This, for example, that the data we record the data from the previous time, and we using the multiple satellite record the data for 40 years, over 40 years. We use the historical data. We didn't run any model. But if we put this data to the model, so very supercomputer model, computer facility, so we get more accurate and more visible, and we can make more effective plan to cope with the climate change problem. And also in Thailand, in our country, we have a problem with the severe drought and severe flood every year, every other year. And during the flood, we use the satellite data, we use the radar satellite to monitor flooded area. I think all of you remember 10 years ago that we have the very extreme flood in Thailand. 2011, so a lot of flood, water inundation over this area. We use the satellite image, so the radar, to monitor the flood extent area. and then try to monitor the flood and to see what the water behavior, water movement from the north to central part and then move to the ocean. And also drought is also very important one. Flood we can monitor, so we can capture the data very obviously. So if we have radar, why we said radar? Because we use the longer wavelength to monitor the flooded area. We cannot use the visible data because the visible sensor from the satellite, they cannot capture the data path to the ground, path to cloud, because cloud obstruction, you cannot get the data. Because optical data, they use sensor like our eye. Our eye cannot see path through cloud. The sensor cannot pass through cloud too. So that's why we need the longer wavelength. Microwave energy, the wavelength is about centimeter or longer. The wavelength is longer, it's bigger than the water vapor molecule and bigger than the raindrop. Then they can pass through the cloud and then can see the surface. That's why we need a lot of microwave data during the rainy season. And also for the drought, during the drought phenomena, it's very difficult to observe it. So it's not like a flood. It doesn't like flood. When flood occurs, we can see the flood. But when drought occurs, who can tell us, who can indicate that is it drought, it's already drought, or what the level of drought? Who can tell us? So it's very difficult to tell it. And we use a lot of the satellite data. One from Thai satellite, and we use more than 10, about 20 satellites from our partner, from the US, from NASA, from the European country, from Japan, from Korea. So we use all of these data to study about flood and drought, and also to monitor the agriculture area. All of these study together, because as I tell you, all of these relate to the area. And if something occurs to the area, like you cultivate, like you grow the plant, so when the flood occurs, we come to the same area. Or drought occurs, we come to the same area that you study. So the area is unique. And then it change over time, change over the phenomena. If something change, like some precipitation change, temperature change, or moisture change, will affect to the area. So that's why we study with the area. And then we study about the variable that affect to your activity on that area. And we use the radar satellite to monitor the flood. And also here, for example, we monitor flood. During the year 2011, the blue color, you will see the blue color in the left-hand side is an area of the flooding. And then a couple of years ago, to like 2021, you see a lot of flood too, but not severe as 10 years ago, not very serious as 10 years ago. And last year also they have flood. You will see that some people worry about the flood will inundate your area. They worry, okay, maybe the big flood will coming like 10 years ago. People will worry about it. But after when we publish this data to compare between the same month during the October, between 10 years ago, last year and previous year, we will see, oh, this situation is much less than last 10 year situation. People feel relieved, and then we see the same picture, and then we can manage it. So people will release, not worry about this too much. Okay, the government can do it, can manage it, can control it when they look at the data. Because sometimes when you monitor the thing, you evaluate the thing, you have to see the big picture. You have to see the big picture, and you will see, when you see the big picture for the whole country, now you understand the situation. You understand how severity of this situation compared to the more severity, and then you will know what will going on. So this is what I said. I try to say that sometimes when we judge the situation, when we judge it, sometimes we use our sense or our feeling. Not use information, right? Our feeling, that means when the summer is coming, you will see that, oh, This summer is the hottest summer that I ever have experienced, I ever seen. This during the drought season or the dry season, you may think that this season, dry season, is more severe drought that we ever seen. For example, like this, people will think that the bad situation will be the worst that we have ever made it before. We ever seen it before. We think like this. But if we have some information, you will see that, the thing that we have experienced this year is not much serious than other year, for example. Like when you feel during your birthday party, you will feel like that, this year I feel very old, older than the thing that I ever have. This year I'm older than others. Right? This is the fact or your feeling. During the birthday party, you will feel, this year, this is the oldest year that I ever have. This is the feeling or the fact. This is the fact, yeah. This older year, but I just compare to our other feeling, right? So the satellite data will help you to evaluate it and to compare it instead of your feeling. So if we manage with our feeling or our sense, sometimes we'll mislead or misleading. This is for example for the flood area. And also, we can monitor the flood area and use the flood area data overlay with the agriculture area, like for example for the paddy field. Then we can evaluate, we can see how much evaluate or measure how much damage that will occur on that time. And also, this is the map you can monitor during the flood area in Jeddah. And also now we move to drought. Drought, I said, is very difficult to tell it because it's slow onset, it's kind of slow onset. We don't know when it's coming. It feels like it's becoming, but we cannot adjust. But we cannot judge, but we cannot tell if we have the guy who made the decision. For example, I have to make the decision to announce that, okay, now is the drought, serious drought occur in Thailand. What the data that we can use? Which data that we choose to be my background, my base to announce it? We need the scientific data. And for the drought, because drought is very difficult because they have the many definitions. For example, meteorological drought, thinking about the amount of landfall. Hydrological drought, thinking about the water in the stream. Agricultural drought. What is the agricultural drought? Now I am stay in the Kasetsart University. I cannot tell you about the agricultural drought because all of you in this area know better than me about agricultural drought, right? I'm kind of reluctant to tell you what is the agricultural drought because all of you know better than me, right? What is the agricultural drought? Okay, for the meteorological drought, thinking about precipitation. Hydrological drought, thinking about the water stream, right? And how about agricultural drought? Thinking about soil moisture. Yeah, I saw all of you say soil moisture, right? I saw you have the correct data. Yeah, you get the right answer. Yeah, I saw your eye. Yeah, thank you. And another thing, socio-economic drought. Which one should I ask? I don't know to socio-economic because they're thinking another factor, another parameter for socio-economic drought. And then, but for me, for us, for remote sensing guy, we did not use this parameter. But when we want to see the drought in agriculture, we will monitor some index that plant or vegetation reflect or respond to this scenario. For example, you're thinking about soil moisture, but when you're thinking about soil moisture, this is not plant itself, right? You're thinking about the environment of the plant, right? Other effect that been influence to the plant state. When you want to measure the plant state, you have to measure by directly to the plant. This is my idea for remote sensing guy. Thinking about direct measurement to that target. You study agriculture, measure the tree or vegetation. Like this room, like for example this room. We are in the same environment, same temperature, same light intensity, same time. But I think all of you have the different level of stress. You know, have the different level of stress. Now I am the most stressed person in this because I'm staying in front of you. That means if you measure the light, the temperature, all the thing environment, you will see that all of us will have the same stress level, right? This is for example. We use remote sensing to monitor individual plant or individual area by to see the absorption or reflection of that plant. For example, if some plant have the proper, I will show you later for the water stress, you will see that some plants show they have some high severity of water stress because we use the near infrared data and middle infrared data to see the water content in the leaf of the plant. And then we can tell that this area got stress and some area doesn't. This for example, some area don't. We try to use the scientific data to see the reflectance or absorption of the vegetation effect to the environment. Here, for example, I will pass it. And here, see, we can calculate the evapotranspiration from this. Every single square kilometer or every acre for the agriculture area to see how much water consumption or water use from the plantation. So for the agriculture area, we can calculate the evapotranspiration from the satellite. And then if they have a lot of evapotranspiration and then no water supply, they will get stressed because they need more water, but no water supply. The different color will show you the different color show you the different level of plant state. The warmer the color, the more state occur. Here we can use it to see the severity of the plant state in detail by using the remote sensing data. And also we monitor the water index, not only in Thailand, but we can monitor our friend, our neighboring country to see how severity of the drought in that area. And also we monitor the agriculture activity. We monitor rice, maize, sugarcane, or cassava every week, every 2 weeks. So, and report to the stakeholder or the government. So this data, if you want to know now for today, if you want to know how many acre of paddy field in Thailand with different age, you can know. You just go to the JIDA website, you will see. So for rice, maize, sugarcane, and cassava, you will see it. A different color, you mean the red color, that means the area that the plant already to cultivate it. And the green color is just begin to grow it. So different color, do we see the different age? When you see this color, when you see this data, I just asking you, this data is benefit for you or not? Or if benefit, what kind of the application that you can apply for your activity, agriculture activity. So I just show you, okay, this is a dry field, different age in different area. For example, you know this time a lot of red color in the north inner part of Thailand. That you will know that the farmer will have almost cultivate and gain yield from the paddy field, right? And then they will have money very soon because they will sell their product, right? Production. They will get money very soon. If you are the salesman, you want to sell some equipment, you can go to advertise and sell them. Or for example, because when I make some example for agriculture area, usually I speak very fluent. I can explain a lot, but you know, when I stay in Kasetsart University, I still a little bit shy, you know, because I feel afraid that you already know better than me. So that's why when you see the different color, that means different age of vegetation, right? Different age need different fertilizer, right? Or not? Different fertilizer. Different amount of the water. So that means if you are the private company or the fertilizer selling, you can send your people and to advertise your product to the farmer, for example. And also another thing I can tell you. If you know, I changed my mind. I think I should not tell because it is online and this is the thing that's secret. Secret is not good for the farmer. You know. Okay, if you want to know, just come to ask me. I already talked with Dr. Priya, I think, Ajahn Priya. Okay, next, move to the next. And then we monitor not just only from the satellite, we verify, validate the data with the in-situ measurement when we set up the weather station to monitor and to evaluate how accurate of the satellite signal. That means we quite confident that our satellite data will give you more accurate information. Yeah, for me, I can tell you more than 80% accurate. And also, we know that how much, how many, and how big of the area for agriculture. We know the age. And now we want to evaluate the health state or the healthy of the plant. So as I tell you, but it's really difficult to, because it's really difficult to judge the level of the plant state level, state level of the plant. Really difficult because nobody tell us, okay, how. So that's why we monitor this agriculture field for more than 10 years. And to see the normal behavior or normal state or normal health of the vegetation in this area. And to see and try to start the normal line, like a back color in normal line, to see the standard. If the plant is more healthy than the standard, we can tell that, okay, this year, the productivity of this area should be increased. But if the plant is kind of straight and weak, lower than the standard, we can see that, okay, the product we will lose the product for this year, for example. But we need, for the productivity, we need the ground data or the actual yield data from the farmer. Otherwise, for the crop prediction or yield prediction will not accurate. But we lucky we have the very, very accurate data from the farmer. And then we use this data for the insurance. And also, we use to predict the sugarcane, the yield of sugarcane. And on that year, previous year, like a couple of years ago, the accuracy is about 99% for sugarcane yield. Evaluate the yield by satellite data. So because we lucky, we have the ground truth data, very accurate, the ground truth data. We have very accurate the yield data from the farmer, and then we can generate the model. So now we will move to another topic, the last topic that I would like to say today. So we know the climate change, we know the plant state, we know the effect of the flood or drought to the agriculture area. So, but how can we adapt for those change? How can we adapt? How can we solve the problem, or how can we have some solution for this? Now we study about we set up the project, namely the AAP for Climate Resilient Agriculture. We use all the physical parameter and all the parameter from the field, working together with many departments like GMD, Ministry of Agriculture, Ministry of the Environment and Resource, and also from the university to monitor and to predict the climate scenario and to see the scenario that affect to the paddy field in the next 10 years, next 20 years. And then make some option or scenario to advise the policy maker. Okay, the next 10 years, what we should do. Or some area we have to postpone, we have to change the crop calendar. Some area we have to change the crop pattern. This is the example that we do. Now we start the working team with I think about 7 government department working together, including the new department, the climate change department, which is the new department belonging to the Ministry of Natural Resource and Environment. We work with that. And you see a lot of many factors that we use for agriculture climate resilience. This is, for example, a lot of index here. And then to see the crop yield estimation, we estimate the yield under the different scenario. And also we monitor the flood risk zone for drought and flood. And also what is the final effect to the final yield. Now we move to, I will spend about 5 minutes for the last topic, greenhouse gas emission. Greenhouse gas emission and removal. So, as you already know that agriculture or everything that have chlorophyll, they can absorb carbon dioxide, right? And you already know that agriculture area, particularly for the rice, have like a bad name for not a bad name, bad guy for the greenhouse gas emission, because they blame that in the paddy or the rice field emit a lot of methane. And the methane have greenhouse effect. And this is a greenhouse gas that more severity, more than 20 times compared to the carbon dioxide. So we try to use this data to monitor. Did you believe that agriculture, paddy field, rice field, emit more greenhouse gas than absorb? Did you believe? Do you believe? Did you heard that agriculture, that for the agricultural country emit greenhouse gas? Nobody said agriculture country absorb greenhouse gas, right? Do you agree? I don't know, because I heard it, but my hypothesis, I don't believe it. I do not believe this, because I believe that everything that green, they have chlorophyll, they will absorb carbon dioxide. All right. For example, here, rubber field. We use the SD covalent for the flux measurement to measure the breadth of the rubber tree ecosystem. And you see the lower in the graph, the lower line the negative number. Negative number that mean they absorb more carbon dioxide because we measure the carbon dioxide over the rubber tree. The negative number is mean that rubber absorb carbon dioxide during the sunlight during the day, and during the night, no photosynthesis. They emit carbon dioxide, but they emit just very tiny number, and then we measure this for the whole year, for the rubber ecosystem, and then we see that rubber absorb a lot of carbon dioxide. This for example, rubber tree much more than forest, but no doubt for rubber tree, no doubt because it's a big tree, right? We were talking about the, we're talking about the paddy field here in this area. This is a graph for carbon variation over the paddy area, over the rice areas in Tungkula in Loyet province. And you will see the same pattern. During the day, it absorbs a lot of carbon dioxide, and during the night, emit. During the day, absorb and emit the data. And also we use the satellite data. We use the satellite to monitor it, to monitor the gas over the rice area for the whole country. And you see the map. The warmer the color indicate that rice emit carbon dioxide, greenhouse gas. The red color, but green and bluish color indicate rice absorb carbon dioxide. Because rice using only 4 months for growing season, right? And then the rest of the year, they emit some energy. But they emit, not energy, emit carbon dioxide. But when we compare during the whole season for the whole year, calculate the net carbon offset, it's showing up that rice absorb more greenhouse gas than emitted. This is just research from the Professor Poonpipop, the professor in the Kasetsart University and in that department. So I built his data to compare with the satellite data and then make the map for it. And now we move back to show you the satellite data. Now we use the satellite data to monitor the greenhouse gas data. And there are a lot of satellites that can measure the greenhouse gas. Now it's more than 20 or 30 satellites. By the government. But another thing very interesting is some of the satellites, more than 10 satellites, built by the private company. By the private company, that means they may see something in the future that monitor greenhouse gas might be very popular by using satellite, and then will benefit for the carbon credit. This is my opinion. That when we looking at the trend of the carbon dioxide or greenhouse gas data, satellite data, I saw a lot of the satellites still, and then in the plan for launching. This is a very important one. And next time, I mean, in the near future, we will see a lot of space measuring for the greenhouse gas for the whole planet. So we will see some country emit more data, more greenhouse gas, some country remove more greenhouse gas. And then next couple year or maybe 5 years, we will see like a very transparent method to evaluate the carbon credit. This is the thing that we have seen for the trend. Okay, I think now I'm done with all of my slides. So this is my last slide. So I just like to conclude my slide with the quote of the Socrates. He said 2,500 years ago that we must fly above the earth to the top of the atmosphere and looking to the earth that we live in order to understand it. So now we follow Socrates. And then for the climate change, this is very, very huge problem for us, and we can cope with and we can overcome this problem, not because of our forcing, but because of our understanding. We have to understand it. And also, the thing that we talk from the beginning until now, we're talking about the measurement. So if we cannot measure it, we cannot improve it, and we cannot manage it. That means if you want to know, you have to measure it, and you can improve it, and you can manage it. เดี๋ยวผมพูดเป็นภาษาไทยนะคืออาจารย์ผมสอนมาตลอดว่าอยากรู้อะไรให้ไปวัดนี่ไม่ใช่ไปหาหลวงพ่อนะคือไปวัดเนี่ยวัดนี่เลยนะครับเพราะถ้าเกิดเราวัดได้เราจะ manage ได้ครับขอบคุณมากครับ thank you very much
Thank you very much for Dr. Pakorn Petpayun for your valuable and informative presentation. Actually, that we give insight for, extreme event, particularly for flood and droughts, that has a lot of impact for agriculture. And now he present us to see that we have a new technology that we can capture flood or either for monitoring drought. Then after that, we can know what we can adapt for our agricultural production. That is very good key message for us. And I hope that our young generation have inspirations from our two guest speakers to interest more to study about climate and agriculture. So before we start for discussion or even for question session, I would like to say that welcome for all audience in the room to take a break and please come back to your seat during we have discussion. And by this time, I would like to invite Professor Simon Wang and Dr. Pakorn on the stage, preparing for the question and some general sharing an idea or also like summary of our presentation for today. Yes, we can have a break for a minute. And also for audience, please take a break. You can have a self-service for the break and come back, and we will start for a discussion session. I would like to announce to the online participants, also please welcome to share an idea, and also welcome to write your question in chat box, or also raise your hand to ask question directly. During this break, you can chat, you can write the question on chat box also. We will try to gather all questions from those in on-site and online participants.สำหรับนิสิตที่อยู่ในห้องนะคะเชิญรับประทานเบรกได้นะคะเทคเบรกแล้วก็สามารถนำมานั่งฟังได้ค่ะ สามารถไปหยิบมาก่อนได้นะคะค่ะ Okay, I will delete message to online participants. So we will come back for the discussion sessions around in 10 minutes. And for questions, I will welcome you to raise your hand, and then we can unmute your microphone and you can ask the speaker directly.
รู้สึกว่าเสียงมัน
1 2 3 Hello.
Feel like this is the government grilling session.
Okay, so we'll welcome you back for the last minutes for our discussion, sharing idea and question. So maybe you can turn camera to our speaker. Is that okay? So first of all, I would like to remind again that for the first presentations from Professor Simon Wang about facing climate risk and events, that he highlights about the extreme event and how it occurs, how we know or prediction for the extreme or risk. For the second presentation is about the extreme event that has impact on agriculture, particularly for drought and flood. And also Dr. Bagon also mentioned a little bit that's very interesting issue about carbon emission and how agriculture can capture or trap carbon that we can trade for carbon in the future. So by this presentation, I would like to welcome from the floor, both in this room and also from on site, to share an idea. Also welcome for any question and discussion. Again, I would like to say again that for online participants, you can raise your hand and our team will unmute the microphone and you can ask questions directly to our speaker. And also, participant in this room, you also raise your hand. We will pass by microphone to you and ask question. Also, welcome to type your question in the chat box. I can read questions and ask question to speaker also. Okay, please welcome. Although waiting for questions, maybe I will invite two speakers to maybe just wrap up or summarize that you would like to say more about the presentation or some additional talk. Please welcome.
If there's no question. Yes. I think there will be questions.
There is online question.
Question from the audience.
Okay, please.
Hello. I have a question on, actually I have several questions, but maybe I'll just ask one and then I'll ask the rest later. When you spoke about the models, Professor Simon, where you said that there are some things that are occurring now that were predicted by the models to occur in 2050. The results of the, I would say maybe wrong prediction, is it because of insufficient data or is it because the data that has been used to predict is just local data and not data as a globe?
Okay.
It's not global data.
Yeah, for that particular example, so you're referring to the example I raised about the London heat wave, the UK heat wave last year. And for that particular case, the reference that I mentioned about the wrong prediction, the wrongful prediction, is not really the prediction per se. It's the interpretation. Because the prediction was made by one line as a mean. From what? From multiple simulations, roughly 50 simulations. So if you have done those type of things, you know that if you plot them, you cannot plot 50 different lines of an increase. And then usually people represent the data in the form of a spread or a range of uncertainties. And then, but normally when people read a report or they just say the media interpreted the report, they see that one line only. So they think that, oh, that's the mean line that touched 2050 at the temperature that was reached last year. So they say, oh, it has happened before, but they fail to read the range. So what the range means is that there's a possibility or probability if the range reaches last year, it means that it's starting to become probable or more probable, more likely that will reach an event like that. So it's somewhat like that. The more recent example I saw is the financial projection. Let's just say you put money in the investment account and your fund manager will give you this projection all the way through when you retire, how much the money will grow. Then they will give you this range as well, because financial downturn, upturn, stock market increase, decrease, like that. So they give you this range. So in that particular example, it's not about the source of the data. It's just how we interpret it. But the source of data could lead to wrongful prediction as well. Thank you.
Okay, thank you for questions. So welcome for the next questions, please. Is there any questions from online participants? No. If not, that I just would like to ask. Okay, online, please.
Hello. Hi.
Yes, Dr. Tiwa, yes, please.
Thank you. Good afternoon, everybody. I'm Tiwa Bautong from Economy Department. Now I live in Kabangsang campus. I would like to say thank you all the very good presentation. But I have a small question for Dr. Bakon. So my question that is it possible to calculate carbon dioxide absorption for another crops, such as corn? My question, I would like to explain a little bit more because I know in Thailand we are very successful to comparison the satellite image data with rubber plantation in case of carbon dioxide absorption. But we don't have the monitoring tower in corn. So I interest your technology, I mean, using the satellite image to monitor the carbon dioxide absorption in corn plantation. It is possible.
ครับขอบคุณครับอาจารย์ทิวาครับ thank you very much Dr. Tiwa. So we have tower for rice, paddy field, sugarcane, but you're right, we don't have the paddy tower over the corn area. So now the satellite data, as you know, they can monitor the carbon dioxide absorption or emission for everywhere in around the world. The data that we observe is just monitor the signal that carbon dioxide absorb energy during this wavelength. We see the absorption over the corn, but the data to validate the amount of carbon dioxide absorbed in this area, we cannot validate now. But we use the equation that we apply from the rice field and sugar. But in the future, I hope it's very near, maybe next fiscal year, we will get the budget and set up the tower station SD covalent over the corn field, and then our data and our equation will be more reliable and more accurate. So I hope I answer your question.
Okay, thank you very much. I hope in the future, as you mentioned, if it's possible to join your project. Thank you very much.
Yes. So may I have a question for Ajahn Tiwa? So I ask if you have any instrument or any plan for set up the new AD covalent tower. Please consider this area, and also we can work together and we can use the satellite data to support the project that we work. And also because right now we tend to have a lot of carbon dioxide data from the various satellite, and then if we can set up the cloud measurement, it would be great, and I think we will have the success carbon map or carbon atlas over the whole country.
Okay, thank you very much.
Okay, thank you very much for both questions and answers. So welcome for the next question. Is there any questions from, yes, please again, yeah. Very happy to see your hand too, yeah.
So I was just wondering, you've spoken about the effects of rays coming in, right? And I was just wondering, is there any effect from underground? In January, there was a news where they were talking about the Earth's core rotation and that it's possibly slowing down or possibly it has stopped. Do events deep in the Earth's core affect weather events on the ground? For any
For both,
any
for
of the
both
two.
speakers, yes, please.
Tell me a little bit. Usually, the effect of the geological process on climate only come from one source, that is volcanic eruption. Now, earthquake, not titanic movement. Those have very tiny effect in the Earth circulation. Even with volcanic eruption, it takes months before the blockage of radiation to take place on the Earth's temperature or mean temperature on that. So, I hope that answers your question.
Yeah. Dr. Burgon, do you have any additional idea to share? Yeah.
I just said to Dr. Simon that I agree, and a very interesting question. Yeah, right now it's in my mind. I'm just thinking about the volcanic eruption. This one is the most another factor that might affect to the climate change. So the same answer that Professor Simon answered. So now I have I would like to see I would like to get some question from the young generation.
Okay.
The
Yeah.
even you can speak in Thai or
Yeah.
English or Japanese language, whichever you like, you comfortable, you can ask. Yeah.
Very good offer. You can ask in Thai, Japanese, Taiwanese, Mandarin, US. Okay, very good.
You say that satellite become the part and have many application agriculture that use satellite in normally in the back day. And I want to know, you say that the cause of drought in agriculture and it have many drought like climate. And I want to know about how the satellite can say how different about drought from climate or agricultural drought, or can say anything about low mineral, less minerals, or high for this can help the farmer to, and to know that this place can plant or need anything to grow their field like that.
Yes, thank you very much. Very challenging question. So this is I really like that when you listen the lecture or some speaker tell you and you feel you can find some gap that we did not explain you. So one thing that you're thinking about drought, as I understand your question, drought is it because of from climate or not climate, right? Yeah, this one is all of the extreme event. Sometimes it's from climate, but some is not. And also now for the climate change, we still try to understanding this because it's really difficult to separate this like a very severe drought or very severe flood. This due to or because of climate change or not. Because sometimes it occur because of during the weather variation. Yeah, this is very hard to identify. But sometimes we can identify if we get more and more data, we will see the tendency or we will see the pattern is change. If the pattern is change for a long time period, like not just only 1 year, but the pattern of drought change or the crop calendar change or the effect of the precipitation change, all of these change for the long time period or the pattern completely change and irreversible. That's one need from climate for sure, right? But for now, if you just observe only 1 year, and then we see that a very big severe flood or severe drought, very hard to tell that it's because of climate. Maybe because of the weather variation. Yeah. But now we try to understand. And what another question that you asked? The second one?
I think the question is about how to use satellite data to monitor drought, right? How to know that which one is like gonna be like meteorological drought, hydrological drought, or agricultural droughts.
Oh, we want to know that. Which one is a hydrological drought?
How to use satellite.
Oh, how to use
show
it.
us.
Yeah. Oh. Meteorological drought is easy to observe by satellite because the satellite can monitor the amount of rainfall. Yes, and then they have the definition that if the rainfall is stop rainfall for how many days consecutively, we can tell that this is a drought, already drought. And for the hydrological drought, we can measure the stream flow. If the stream flow lower than the standard or something happen, we can tell that this is a hydrological drought. And for agriculture drought, like I argue, how can we can know that agriculture drought? And then Ajahn Parichat helped me to answer that this is soil moisture. Soil moisture we can measure from the satellite, and we can tell that this is agriculture drought. And another drought that I already explained during my talk. So we try to monitor like the real or the vegetation index or the drought index. Drought index, that means we use multiple factors. We use multiple like soil moisture, vegetation index, air temperature, surface temperature, and then we try to indicate indicate specific drought for particular area or particular activity, like a drought in paddy field area, drought in sugarcane, drought in corn. This depends on the type of the crop that we monitor. This one, satellite can do it and can monitor it. And now this year, we apply drought index for the paddy, for the rice area, for the whole country, in order to monitor and compensate, make some help to the farmer. We're working with the TMD and Ministry of Agriculture and JIDA work together by using this index. So hopefully this one that I answer your question.
Thank you very much.
Okay, thank you very much.
Thank you for the question. I'm really impressed.
So you feel happy because young generation already asked very good questions to
Yes,
ask.
I should not ask her because she asked very hard question. I think quiet.
Tough question. But anyway, I would like to know more than that. Can we use satellite to predict drought or flood? Or we just know only when it already happened? So maybe this question will ask for both Dr. Pakorn and Simon, because I would like to ask Simon too, is it very difficult to predict extreme event? Yeah.
It is very difficult. It's never easy to predict anything. But extreme events happens when the conditions are right. And also there's an extra ounce or extra force from the conditions that you just don't see it coming. So satellites, just like sensors, they see things after they happen. Drought for example, and flood. When you start to assess the flood damage, you use satellite to see a bigger domain with better precisions. But by that time, flood has already happened. So what it is the tool for prediction? You only come from two things. One is experience. What past weather has led to. Just like we make all the decisions based upon our experience, right? If you have a 7:30 a.m. class and you want to make it so now late. You have the past experience to know the traffic conditions, before 7:30 a.m. and stand for maybe for Tuesday, then it's 10 a.m. Now the traffic condition will be different. So use that as a prediction. But you cannot expect if there will be accidents on the road that delays your commute. The same thing for weather. Climate is more like a long statistical property of weather changes. So that's something we can use. With enough satellite data, long enough satellite data, you can see the pattern, then you know the seasonality, then you know what past season has become. For example, if before the monsoon happens, there has been a abnormally wet spring, then you know the soil moisture content is high. And when the monsoon starts to fall and it falls a lot, you can see that the flood potential is going to increase. So that's kind of experiencing adding up. The second tool is computer. What computer does is it can calculate based upon the physics, what would project into the future based upon observations that we got right now. And it is not different from stock market prediction, market projections, medical predictions, like how the doctor going to say how your cancer may spread, and based upon experience and also based upon modern computers with data. So those are the two tools that we can use. The more data, the better. So we're always data thirsty. Thank you.
Yeah. Yes, thank you. And I would like to say, I would like to add some answer from for Ajahn Noi, and I agree with Dr. Simon. So experience and data and computer, and also now we try to use, try to analyze the data, try to transfer our experience and our data to computer, like try to use machine learning and AI, try to calculate the whole data that we already record for the long-term historical record, like a 40 year in Thailand, and try to see the pattern of flood, and also try to see the pattern of the weather, and then combine with the weather satellite to see the real-time weather satellite to see when the typhoon or the storm will hit to the area or hit to the some particular area in Thailand or on the land. And also we compare to the historical flooded data. So we'll see the possibility or the likely flood will occur in this area. Because we record the satellite data both for the precipitation and also for the flooded area for more than 15 years or 18 years. And now we see the pattern. We can see that like for the Lafley area what will occur. So we use the weather satellite and then use the radar satellite to monitor it. And then we apply the satellite data with the water level gauge. So to see the water level in the river or in the canal important, and to see which area will reach the higher level that will overflow the bank, and then we can calculate the potential effect area for the flooding. So we apply this since last raining season, and then we will apply this again for next rainy season, and then we will use the machine learning and AI to try to monitor it. But the most important thing is right now the experience, and how can we transfer from human experience to teach computer.
Yeah, thank you very much. So we have a few minutes of time. So welcome for one questions on site, and if have more one questions from online also possible. Yeah, please. Yes. Wait a minute for microphone. Yes.
Sorry, I just had a follow-up question. Is human activities also factored in the data? Or is it just weather data that is being collected and human activities are not factored in?
I'll have to clarify the question. Do you mean human activity of?
I mean, in the rate of production of, let's say, greenhouse gases.
Okay.
Is that factored in the
data? So, well, it's actually not the same question. The previous question is about the natural occurrence of events, right? And your question is connected to that question in the sense that if you see a long-term change, then does human activity contribute to that? In the line of the analysis or research like that, we call it attribution analysis. Like you say, oh, you know, there used to be 2 months of rainy season in Bangkok, but then over the past 10 years, we have seen a quadruple increase. Does human activity contribute to that? And that's different from why there is a rainy season or why there's a storm, because that's a meteorological natural process got affected over time by this human activity impact. So if I understand your question correctly, that's what you meant, right? So yes, human activity does affect the data it collects, but just on different level. For example, if you constantly measure temperatures every day at the same time, and over time, the temperature increase will contain the results from the human activity, such as aerosol, such as greenhouse gas. So you're going to see the change in those things. It doesn't mean that the data is contaminated by the human activity. I mean, it's just temperature. It's temperature. It doesn't really contain anything else. It's what it measures that has the contamination or influence from the human activities. If you extrapolate that to precipitation or the rate of precipitation or the spread of precipitation, and it will come to the same conclusion, that the change in the behavior of precipitation may contain human activity. But how much is that? It's really open to research questions. You know, it's not indifferent. The way I see it is, we have a lot of, I mean, in the medical world, there's a lot of theory about what you eat that may contribute to cancer. And with enough data, clinical data, you can pretty much say, okay, if you eat too much of this processed food, then it's possible or higher, more likely you're gonna contribute to cancer. But if you pick up one person, let's just say you and I, there's not many other things in our life that will also lead to cancer or prevent us from getting cancer. And that becomes very difficult to track. So if I understand your question right, you were talking about the long-term change. But if just for one day event, the data is just the data. The human activity contamination or the role of it is really small. Okay, thanks.
Okay. Yes, please.
So just would like to share some experience of some knowledge from the agronomy side. So I mean, I think for the using the climate data or satellite data for the prediction or for the management of the crop production, I think the bottleneck of our Thailand, I think is cloud truth data or cloud data from the farmer or from the production side. So if we can get enough data from the cloud truth, I think that can make the more efficiency or more accuracy for the how can we use the climate data for using the prediction our farm production or crop production. That's it. I think now Thailand is the lack of the good data or informative data from the farmer side. So I think this one is our bottleneck from now on. For we have to booting or we have to do a lot of data from this side. Just my experience. Yep. Thank you.
Okay, thank you for sharing your idea. So yeah, please.
Okay, a question for Dr. Pakorn, because you talk about carbon emission from the plants, it's just curious, because people talk about carbon emission lately, for the global warming, those stuff. However, just curious whether you can compare, let's say, carbon emission from the plant, from the, for agriculture process, compare with other sort of carbon emission, how much or how small, compare with other source,
Thank you, Professor. So you mean compare amount of carbon emission from different land cover, right? Yep.
Compare with, let's say, from the industry, from the area, I'm just curious whether this is a big factor for the carbon emission, from the plant.
Yeah, actually we can compare because satellite fly over every area, and then they will have the same sensor and same standard. We can compare carbon emission or removal for any different land cover and land use type. But in the city, land, on factory or agriculture, forest, we can compare for every land use, land cover type. And also, we can see how much variation, like a temporal variation over time in different areas. Like a different season, you will see in the same area, they will emit lead or emit mud or absorb lead or mud in that area. So this answer, I quite confident that we can compare for it. Yeah. And also, all of this data, because we do the same sensor, like one satellite orbit around the Earth, that means we have the same standard to measure, right? That means we can see that how much it emit and how much it decrease with the relative. We can see compare like a relative number.
My question is, can you compare right now? Do you know the answer?
Yes.
Right now,
yeah.
how significant carbon emission for agriculture compared with other sort of carbon emission? Can you compare right now? Do you know the answer?
I can answer you just like if I say percent, I can answer you like more than 50%. If it's open source, not carbon emit from the closed area like a factory non-poisson, we cannot measure it. But like and it's from the from different sector, if we can monitor from from the traffic sector, agriculture sector, power plant sector, we can monitor it. But it's some sector that is not like an open source, we cannot monitor it. So some sort we cannot. And also one thing that we're not sure that if some area emit the greenhouse gas source with the mixing land use, land cover type, like a not homogeneous area. You see for this like a power plant, and this one a factory, and beside of the big agriculture area, for example, this one will mix together. That we try to avoid this area because it's not homogeneous. And then for the can I say the spatial resolution of the satellite data is not far enough to separate between individual power plant or individual factory. You know what? This is the thing that limitation for the satellite from now.
Okay, so because unfortunately we have time out, so is there any questions from online? No. If no, I hope that we can have more discussion later individually after this session be end. So I hope that the two presentation today will give us to have some idea that how we can move forward to working about agriculture and climate change or climate extreme that help us to get better adaptation under the fuel climate change in the future, and also how we can have better resilient. That's the words that Dr. Pakorn mentioned today. That's very good word for agriculture. So I hope that everybody enjoy, and I very enjoy and have high new information and knowledge from today's presentation. So lastly, I would like to say that I'm very much appreciate for both Professor Simon Wang from Utah State University and also Dr. Pakorn Petprayun from GISDA. So please grab your hand and thanks for both two speakers. So also thank you very much for all audience and participants from both inside this room and also to join us from online. I think very appreciate for you all too. Thank you very much again and hope to see you all for the next planned forum session in the next year, like annual KU conference 62. Okay, thank you very much and have a good evening. ขอบคุณมากค่ะ